We next look at the problem called pattern matching. This is something I am sure you've used before. Okay, so the problem is this: you're given as input a text and a pattern. Okay, and you want to find if you want to determine if this pattern occurs in the text and where. Okay, output is find an occurrence of the pattern in the text. Okay, you could change this to say find all occurrences. It really doesn't matter. Okay, for the time being we concentrate on this. We want to find an occurrence of this pattern in the given text. Okay, grep is something that does this. Okay, so I guess if you've used Unix, if you use Unix, then the command that does this is grep. Right, you can grep for a string in a file. So you can take a file and a string as input and look for the string in this file. And I'm sure every other operating system provides this facility. It's a very basic sort of facility which is provided and which is used quite extensively. Okay, so what we're going to do is design an algorithm for this problem. Okay, which is given a text and a pattern, find an occurrence of this pattern in the given text. Okay. Okay, so what's the first algorithm that you would write? Well, you take this text, you take the pattern, okay, and you sort of look for the pattern at every possible position in the text. Okay, so the text is say n characters long. Okay, you start at the ith character and check whether the pattern there is an occurrence of the pattern starting at the ith character. Do this for every I. Okay, so for every possible position, you check whether the pattern does in fact occur at that position. Okay, you could do this in a loop. Okay, so you can sort of scan the text character by character and starting at from left to right say, and for each character from this character onwards does the pattern exist. Okay, so you check for this. Okay, so symbolically let's say this is the text. Okay, well, and that's the pattern. Okay, I start matching character by character here. If there is a complete match, then I know that the pattern occurs here. Okay, if it doesn't, let's say there is a mismatch somewhere here, then I shift the pattern by one character, okay, to the right, and now I start comparing from the second character onwards. Okay, I check whether the second character of the text equals the first character of the pattern, etc. So I check whether the pattern occurs here. If it does, I output. If it doesn't, I again shift this pattern by one more. Okay, and so on. So each time I sort of shift the pattern along the text. Okay, and well, when the sort of pattern is at some place, let's say here. So this is the pattern, and that's the text. I just check whether they match character to character. Okay, I just check that these two characters are the same. If all of them are the same, then I have actually found the pattern here at the text, and I can output this index. Okay, this is where the pattern occurs. So this is sort of a naive and sort of the first thing that you would do, the first algorithm that you would come up with to search for a pattern in text. How much time, I guess, is the question that we've been asking throughout this course, and we will ask again. So how much time does this take? Firstly, this can be sort of written in I mean, I hope all of you can write code for this naive algorithm. just put it in a loop and you sort of move the pattern across the text, right. So this you should be able to do, and if you're doubtful, I would suggest you just try this before we proceed further. Okay, yeah, then we come back to this question: how much time does this take? Well, you compare. Let's say the size of the text. Okay. Let's say the text has so the text has n characters, and the pattern has m characters. Okay, the size of the pattern is m, size of the text is n. Then for each starting point in the text, we search for the pattern. Okay, so in the loop I have to check for starting with n characters, and each time, and the worst case, I may make m comparisons. So the total sort of time is OMN. Okay, this is the total time. Okay, this should be clear, because for each of these n characters, when I start, when I start comparing from here, I could go most of the pattern. I could sort of go down most of the way and then perhaps discover a mismatch. In which case, the total time taken is OM for each of these indices, and there are ON indices. So, well, the total time is order MN. Our objective is to, can we do faster? Okay, so this is the question that we would like to address, and in fact we will do faster. Okay, so by the time this lecture ends, you will see that we can do much faster than OMN. Okay, that's the objective. Okay, to see how do we go about doing this, the first thing to do is to check out a few examples. Okay, which is what we will do. So we will take some patterns, some simple patterns. We will see how would one search for these patterns in a given text. Okay, so let's say, so here's sample 1. Okay, so supposing my pattern is A B to the K. Okay, this means it's A B B B. Okay, there are K occurrences of B. Okay, you can take K to be 20, for instance. The real exact value of K doesn't matter, but the pattern looks like this, and you're searching for this pattern in a text. Okay, so yeah, so let's just see what happens here. Okay, so let's say this is the text. Okay, and you've started searching from this point onwards. Okay, so it's A. This is the pattern. Okay, you started searching from here, this is A, let's say. So there's a match, then you sort of check, maybe this is also a match. You go down, a few characters, they're all matches, and then there is a mismatch. So here I have a mismatch. Okay, before the pattern ends. Let's say the pattern ends here. Okay, so somewhere here is a mismatch, which means this is not a B, right? I know that this is not a B. Okay, now what can we do? Well, the naive algorithm, what would the naive algorithm have done? It would have shifted this pattern by one character and then started comparing, right? This A would have been compared against this B. You would have immediately gotten a mismatch, and then again go down one more. You would have you will again have a mismatch, because, well, all of these are B's up to here. Because the pattern is matched so far, all of these are B's. Okay. In fact, so all these, when I start shifting, all the initial shifts are useless in a sense. Okay, because when I shift by, let's say, this amount up to this, I know this A is going to have a mismatch with the B. So I'm going to start shifting again. I'm not going to find the pattern. So the pattern, this pattern is certainly not going to start anywhere here. If at all, it's going to start here. right. So, if there is a mismatch, I can, for this pattern, I can move this all the way up to here. Okay. So, I can start comparing here now. So, I move the pattern all the way here and I start comparing. I do not need to sort of shift it one by one, I can shift it all the way here and I start comparing. Okay. So, there was a mismatch at this position, I move the pattern all the way and now I start comparing. So, for this pattern, this algorithm works. So, I start comparing, this text and the pattern. Okay, here is the text and pattern, and if there is a mismatch in the ith position of the pattern, I just move the pattern all the way up to here and I start comparing now with the first character of the pattern, right. So, essentially we have somehow used the fact that the text has matched the pattern up to here. So, we know that these are all B's, okay, and that my pattern must start with an A. Since there is a mismatch here, there is a good chance, there is some chance that there is an A here. So, we cannot sort of move it even further, okay, this is what we move the text up to. Okay. So, supposing we follow this this algorithm for this pattern, if there is a mismatch, I move it all the way here and now I again start comparing, I compare this with A, I go down here, suppose there is a mismatch, I move the pattern all the way here. So, how much time does this take? Okay. Well, this is a crucial argument, because some such argument we will use in general. Well, the total number of comparisons, by time we will just say the total number of comparisons is actually 2n, at most 2n, at most 2n comparisons. Why is that? Well, we look at each position, okay, of the text. I claim that for each position of the text, I will make at most 2 comparisons. Okay, why is that? Well, let us see. We start here, for these positions of the text, I make only one comparison, because once there is a match here, okay, once there is a match, I never make any more comparisons for this position in the text. If there is a mismatch, I may make one more comparison, which is the pattern shifted all the way. Now I match A with this. If this does not match, I shift the pattern and I move ahead. So, for each position in the text, I make at most 2 comparisons, right. So, the time here, the total number of comparisons that I make for this, that I need to make for this pattern is 2n. Okay. So, well, there is a glimmer of hope that maybe we can do faster than m times n, right. So, let us take another example, again a simple example, but this will again illustrate what we are trying to do. Okay. So, example 2. So, earlier we took a b to the k, let us now take a to the k times a to the kb, which is nothing but a k times followed by b. Okay. This is the pattern we are looking for in a text. Okay. So, how much time does this take? How many comparisons do we have to make? If we sort of do things not just naively, but in an intelligent way. Okay. So, again let's see what happens. So, here is my text. Okay, I start comparing, let us say from here. I have done all the way up to here and I am sort of comparing from here, and well, let us say that is the pattern, okay, and I have a mismatch here. Okay. So, I have a here all the way up to b. Okay, this is the pattern. In the text, I know that I have A's here. Here there is a mismatch. Okay, this could be anything. This is a mismatch. Well, what can I do? Okay, so in the naive sort of thing, I would have shifted this by 1, right? This would have shifted by 1, and I would have started comparing again, and you know that again there will be a mismatch here. Okay, there will be matches all over here and there will be a mismatch here. Okay, this is known because I know what the pattern is. So, if you want to do it intelligently, you know that starting the pattern anywhere here all the way up to here is useless, because I need string of size A's of size, there should be k A's and they do not occur here. This is not an A. So, I can in fact start the pattern right here. So, once there is a mismatch, I can start comparing right here. Okay. So, I can move the pattern all the way after the mismatch. Once there is a mismatch, I just move the pattern up to here. Okay. So, I know, because the reason is I cannot find the pattern anywhere here. Okay. I have to start here, because the pattern has to start with an A and then I need to see k A's, and I do not see that here. This is not an A. Okay. So, again I have used some information about the pattern to move the string all the way. There is one more case here, which is when the mismatch is at B, but before we do that, okay, maybe we will do that and then come back and see how much time it takes. Okay. So, here is my text. Okay, now the mismatch is here. Okay, so this is a mismatch. So, the text matches all the way up to here, except there is a mismatch. Now, what do I do? Okay, so now there is a good possibility that this is A. Okay. There is a good possibility that the place where there is a mismatch in the text, it actually is A, in which case if this is a B, okay, if the next thing is a B, then you will miss, I mean you cannot move it by more than once. Okay. So, I have to try this, the pattern shifted by 1. This is quite possible, A, B. If there is a mismatch at this position, it is quite possible that the pattern occurs here. So, I can at most shift the pattern by 1. So, this looks like a worst case. I cannot shift by more, the pattern by more. This looks like a worst case, and we are back to looking at the naive algorithm. But while we are shifting the pattern by 1, there is something we are gaining. Okay, what we are gaining is that we know that there are match up to this position, there is a match. Okay. While I shift the pattern by 1, I do not have to again match all of these as I did in the naive case. Okay. Remember, the naive algorithm, I shifted by 1, then I started my comparisons here, do these match, do these match, do these match, and so on. Here I do not have to do that, I can start comparing from here. Okay. I shift the pattern by 1 and then I start comparisons here. Okay. So, if this is an A, if there is a match, then I move up again, this fellow moves up again. Okay. This moves, now I see whether this is B. If there is a mismatch, I move the pattern by 1, but the text pointer remains where it was. Okay. So, the text pointer remains where it was. So, how many? Okay. So, I hope the algorithm in this case is clear. It is slightly more complicated than A, B to the K, but I hope the algorithm is clear here. Okay. So, how much time does this take? Okay. So, what is the time? Which means how many comparisons do we make in the case of A to the K? So, let us go over this. Suppose there is a mismatch in one of these positions, I move the pattern all the way here. Okay. I move the pattern here. If there is a mismatch at B, well, I move the pattern by 1, okay, by 1 unit, but I start comparisons here, this text with this pattern. Okay. Okay. Now, of course, there could be a mismatch. If there is a mismatch, then I move the pattern all the way up. If there is a match, then I move this pointer by 1, this pointer by 1, and I compare. Okay. That's the way the algorithm works. How much time does this take? Well, the claim is, again, look at each position in the text. Okay. If I look at this position in the text, then the number of times, okay, the number of times this is compared is at most 2. Okay. If there is a match, then the text pointer moves forward. Okay. If there is a match, the text pointer moves forward and that position is never compared again. Okay, so it's at most once. A match occurs at a position in the text at most once. How many times can a mismatch occur? Well, again I claim that the mismatch will occur at most once. Okay. Well, if the mismatch occurs at a position which is not B, at one of the A's, then the text moves forward. Okay, so this is the case. If the mismatch occurs at one of the A's, okay, then the pattern is moved all the way here. Okay, the pattern is moved all the way up here, and the text pointer which was here now moves up by 1. Right? If there is a mismatch, the text pointer moves by 1. I never compare this again. I never compare this character again. If there is a mismatch at B, okay, if there is a mismatch at B, the text stays again here, but the pattern has moved. Okay. Now check what can happen. Either there is a match, in which case the text moves, or there is a mismatch at an A, again the text moves. Okay. So there can be at most 2 comparisons per text character. Okay, so for each character in the text there can be at most 2 comparisons. So the total time is 2n. The number of comparisons. Okay, so the number of comparisons is at most 2n. Okay, so in both cases we see that the number of comparisons is at most 2n, and this gives us hope that maybe we can do it faster. For instance, it's worth asking, can we do it in O(n) time for all patterns? Okay. So what is the scene? Suppose I should be able to do this. What is the scene? Well, the question is, okay, so if I have this is the text, and I have this is the pattern, and I match some of them, and here I have a mismatch. In each of the earlier cases, we somehow used this matched information. Okay. This information that this portion of the string matches with this portion of the text was used in both cases. So this is what we would like to use. So can we use the match information? Okay, which means the information that this portion of the string actually matches this portion of the text. Can we use this? And this is what we would like to do. Okay, somehow use this information. What we would also like to do, okay, like in the previous case, is try and shift the pattern as much as possible. So here's one goal. So shift pattern as much as possible. Okay. So what does this mean? I mean, okay, so here's my text. We're going to see many of these 2-lane highways throughout this talk. Okay, so here's my pattern. Okay, in fact, if you see this figure, this is a text and that's a pattern. I'm not going to keep writing this text pattern business. Okay, now let's say there's a mismatch here. Okay, now when can I say that moving it by 1 is not necessary? Okay, when can I say that this is useless? Well, this is useless if this portion will not match this portion of the text. Okay, if this portion does not match this same portion of the text, there is no point in moving it by 1. Okay. we in some ways know this portion of the text because it has exactly matched this portion of the pattern. Okay, all this I have a match in the text, up to here I have a match, and this is my first mismatch, which means if this portion of the pattern, okay, this portion of the pattern does not match with this portion of the pattern, okay, forget the text for the time being, just look at the pattern. This is the original pattern and here is the pattern shifted by one character. If this portion of the pattern does not match this portion of the pattern, there is no point in shifting it by 1, because if there is a mismatch somewhere here, there is going to be a mismatch there also. Okay. How about 2? Okay, how about 2 characters? Again, it is the same thing, only now I am concerned about this portion of the text, okay, this portion, and you see that portion of the pattern. In general, so let me draw this again. Well, the crucial idea again is that once I have matched up to here, okay, once I have matched up to here, then whether to shift it by 1 or 2 or 3 or 4, it is only something to do with the pattern, it has nothing to do with the text in some sense, because the text is already matched, right. So, this decision I can make by looking at only the pattern. Okay, what do I mean by this? So, here is my pattern. Okay. So, think of the text sitting up there. I have a mismatch here, and let us say, you know, the best way to do it is to shift by, you know, some I units. Essentially, I do not, by shifting, I do not want to miss an occurrence of the pattern in the text, right. So, that is what I do not want to miss, otherwise I would like to shift as much as possible. So, here is the text. Okay, supposing this is shifted by I units here, supposing, you know, if I is the best you can do. What does this mean? This means that this portion must match this portion, right. This portion, which is a prefix of the pattern, must match the suffix of this portion of the pattern. Okay. This prefix must match this suffix, and this must be the largest prefix. I cannot have a larger prefix matching this, right. For instance, if instead of if I move the pattern by less, okay, let us say I minus 1, then I have and there is a match, then I should not, you know, miss that opportunity. So, what I am saying is this. So, here is my text, okay. So, here is the pattern, and let us say this is shifted by j which is less than I, this is j which is less than I, okay. The mismatch is at the same position, okay, this is the same position as that, okay. Now, I can safely do away with these j's if this is not a prefix, if this prefix is not a suffix of this, okay. So, for all j less than I, this prefix is not a suffix of this portion of the pattern. So, this portion of the pattern is the same as this, okay, these two are the same. So, any prefix which has which is larger than this, length larger than this, will not match with a suffix, okay, then I can move it forward. And essentially I want to, you know, I want you know, the largest prefix of the pattern which matches the suffix at this point. So, if there is a mismatch, that is what I want, okay, then I can move it all the way up to that portion and then start comparing. So, this is what I really want to do, okay. So, this data is only pattern dependent, that is the first thing, okay. So, this only pattern dependent, okay, this data this is the data that tells you how much to shift. And what is this data? Okay. Yeah, so supposing okay, so supposing you have a mismatch at the ith position. Okay. So suppose you have a mismatch at the ith position. How much to shift the pattern by? That's what you want to know. Okay. Okay, so how much to shift the pattern by? Well, so let's look at, so here's the pattern. Okay, this is the ith position. Okay, I have P1 through Pi minus 1, and supposing, okay, supposing I have an optimal shift which looks like this. Okay, so P1 so on, and this is Pi minus let's say T minus 1. So supposing the optimum shift is by T characters. Okay, which means if I shift by less than something, less than T characters, then this is not going to work. I mean, in the sense there will be a mismatch. Okay, so what does that mean? So if it's less than T, so here's my pattern P1 through Pi minus 1. If I shift it by less than T, then there will be a mismatch somewhere here. Okay, mismatch if shift is less than T. Okay, so this means that there is no point in trying out this shift. I might as well shift it all the way up to T, and if the optimum shift is T, this means that I have a match all the way up to here. Okay, which means P1 and so on up to Pi minus T minus 1 is a suffix of P1 to Pi minus 1. Okay, so this is a word, and that's this is a word with I minus 1 characters, and this word is a suffix of this. Okay, that's what this shows, that these two are the same, and so on. Okay, and because there is a mismatch somewhere here, we also know that P1 through Pi minus, let's say, j is not a suffix, okay, of P1 through Pi minus 1 for values of j which are smaller than T minus 1. Okay, so for j less than T minus 1, right. So the value of j is less than T minus 1. So if the shift is less than T, which means if the shift is less than T, then this is not a suffix. Okay, when I shift it by T units, then I have a match all the way, which means this prefix of this pattern is also a suffix of P1 through Pi minus 1. Okay. So given a pattern, okay, what we are trying to do is, for a mismatch, we want to find out how much we can shift the pattern by. We would like to shift it by as much as possible without missing an occurrence of this pattern in the text. Okay, that's what we were doing. Okay, so supposing so let's look at this figure. So supposing the mismatch is at the ith position in the pattern, okay, the text sort of is okay till here, there is a mismatch at this position. How much should I shift the pattern by? And we saw that I would shift it by t units, okay, this is t units, if the following thing holds, which is this prefix p1 through p I minus t minus 1, I minus t plus 1, this prefix is a suffix of this portion, okay, and this is the largest such string. If I cannot, if I shift it by less than this, okay, then there will be a position where there is a mismatch, okay, that is what it says. For all smaller shifts there will be a mismatch. Here I get a perfect match, okay, there is a match between these. So it just says that this is the longest prefix of this string, which is also a suffix of this string, okay. Yeah, I want actually them to be a proper prefix of this, which is a suffix. So then the crucial thing, the thing that we want to find out is this, right. So the first thing is that this quantity is a function of the pattern, okay, and can be pre-computed. So I can pre-compute this value as to for each mismatch how much to shift it by. Okay, so what is this function of the pattern that I want to compute is for each I, okay, for each position, let us say, find the largest prefix which is also a suffix. Oh, I have actually not defined prefixes and suffixes. I hope you know what it is. So given a string, okay, a prefix is all the initial portions, okay, the first I position is a prefix, and a suffix is just the last portion. This is a suffix, and this is a prefix. Okay, so given any string, this is a prefix and that's a suffix. Okay, so given any string, I want to find the largest prefix. Okay, let's say largest proper prefix which is also a suffix. Clearly, if I take a string, the string is a prefix of itself and suffix of itself, right? But I want the largest proper prefix of a string which is also a suffix. So this is what I want to compute. Supposing I have computed this, right? So I have pattern P1 through Pm is the pattern. Let us say Fi is length of the longest prefix of P1 up to Pi minus 2, which is also a suffix of P1 to Pi minus 1. Okay, this Pi minus 2 is just to make it a proper prefix. Okay, so any prefix of this, so length of the longest prefix of this, which is also a suffix of this. I could have written Pi minus 1, but then I will mention the longest proper prefix, right? So supposing I have computed this for each I, for each position in the pattern, I have computed this Fi, which is the length of the longest prefix of P1 through Pi minus 2, which is also a suffix of this, which means if I take any other prefix which is longer, okay, then it will not be a suffix of this pattern. Okay, good. Now on mismatch, at position I, what can I say? Okay, I say that you can shift the pattern by I minus 1 minus Fi. Okay, I can shift it by this much. Given Fi, which is defined this way, then on mismatch at position I can shift the pattern by I minus 1 minus Fi. Okay, so let's see this. Okay, so here is my text. Okay, this is a pattern, and this is, let's say, the ith position. This is the ith position in the pattern, and there is a mismatch. Okay, now I know. Okay, so let's see what this says. This says Fi is the length of the longest prefix, which is also a suffix. Okay, so if I put that down here, so this is the string that I am considering now. Okay, I am only looking at P1 through Pi minus 1, right? The mismatch is at I, but I am looking at P1 through Pi minus 1. Good. So this is the string I am looking at, and I know that which is the longest prefix of the same string, which is also a suffix. This I know has length Li. Okay, which means if I move the pattern all the way up to this position, then there is a match here. If there is a match here, I know that the text has matched everywhere here, so there is a match with the text. I also know that this is the longest prefix, which means if I shift it by any less, there will be a mismatch at some position, which means there will be a mismatch with the text, right? So the amount I move is this, the amount I shift the pattern is this. This is I minus 1, right? So the amount I shift the pattern is I minus 1 minus Li, which is what we had. Sorry, Fi. This is Fi. Sorry. Okay, this is Fi. So I must shift this by I minus 1 minus Fi, right? So this is what I had said in the previous step. So once I compute these Fi's, if there is a mismatch in the ith position of the pattern, if Pi mismatches with the text, then I just shift the pattern by I minus 1 minus Fi. Okay, and I start comparing now. Okay, so let's write this code down and see what this turns out to. Okay, so initially I am looking for a pattern in a text, right? So the pointer to the pattern I will refer by X. Okay, the pointer to text I refer by Y, the variable will be Y. Okay. Initially, my initialization is X is set to 1, Y is set to 1, and I start comparing. Okay. Now, what does the generic step look like? So if P of X okay, is a text at Y. So this is a text. Okay, this is the pattern. If there is a match, okay, then what do you do? Well, I need to increment X and Y by 1 and then continue. Okay, then X is set to X plus 1, Y is set to Y plus 1. Okay, and I continue. Okay, I will have to go back and loop. Okay, what happens otherwise? If there is a mismatch, then I know that I must shift the pattern by this much. Okay, I shift the pattern by I minus 1 minus Fi. Okay. So, this is where the mismatch is. Okay. So, this is where my y is. Okay. This pointer on the string is y. Okay. The pointer in the text was I here, right. Now, what do I set it to? I set it to fi plus 1. If it were I initially, I set it to fi plus 1. If it were x initially, I set it to fx plus 1. Okay. Because I have moved it by I minus 1 minus fi, okay, or I minus 1 minus fx. Remember, my pointer was x here. It was not I but x. If there is a mismatch, I shift it by x minus 1 minus fx. So, the next character I am going to check in the pattern is nothing but fx plus 1. Okay, so, let us do this. So, else x is set to fx plus 1. Okay, this is what I want to do. There is just one case that we need to take care of, which is this actually is true when x is not equal to 1. Okay. So, this is when x, else if x not equal to 1, then you do this. Okay. Now, if x equals 1, okay, what does this mean? That means the first character of the pattern, there was a mismatch with the text. I am comparing the pattern with the text. If x equals 1, it is the first character, right. So, the first character of the pattern mismatches with the text, then I just move both pointers. I move the pattern by 1 and I move the text pointer by 1. Okay. So, let me write this. So, all this sits inside the else. So, if x equals 1, okay, then y is y plus 1. Okay. So, I just increment the text pointer by 1. Okay. So, all this sits inside the else. So, this is inside the else and the whole thing is in a loop. Okay. When do I have success? When do I stop? Well, I stop when x becomes size of p plus 1. Okay. So, let me write that. So, success if x is size of p plus 1 or m plus 1. Okay, which means I have matched successfully the m positions of the pattern, then I have found the pattern in the text. Okay, this is the success and the whole thing is in a loop. So, in a while loop you can check whether x is p plus 1 or not. Okay. So, this is the procedure, this is the algorithm given fx. So, this function fx for each fi for each position I, then the algorithm for searching this pattern in the text is this. And now let us see how much time this takes. Right. So, what is the time? Okay, the time, let me quickly write the main loop again. Okay, it says if px equals ty, then x is made x plus 1, y is made y plus 1. Okay, else the crucial step is if x not equal to 1, then x is fx plus 1. So, you have shifted the pattern. Okay. If x equals 1, on the other hand, then y is y plus 1 and then you loop. Okay. This is the algorithm and then you check for success. So, how much time, how many times, how much time does it take? Well, it is the number of times this is executed, right, number of times these statements are executed. So, how many times are these executed? Well, I can count number of comparisons. This will tell me the order, okay, of the algorithm. Now, the number of comparisons that I make totally over is nothing but number of successful comparisons, okay, which is number of matches plus number of mismatches. Okay. So, now let us look at each of these in turn. This is very similar to the merge sort. Okay. So, I would, once you look at this analysis, go back and check out merge sort. Okay. So, now what is the number of successful comparisons? Now, each time there is a successful comparison, y increases by 1. Okay. Check out that y increases by 1, y never goes down. Okay. The pointer on the text never goes back, always goes forward. So, the number of comparisons, each time y goes up by 1, it starts at 1, ends up at n. So, this is at most n minus 1, because y, the smallest value is 1, the largest value is n, and each time there is a successful comparison, it increases by 1. Okay. How about number of mismatches? Well, in one case x drops by at least 1. Okay. In the other case, y increases by 1. So, if I look at y minus x, okay, if I look at this function y minus x, okay, this always increases when there is a mismatch. If there is a match, y minus x remains the same, right? Both of them go up by 1, nothing happens to this. If there is a mismatch, this increases. Initially this is 0, the largest this can be is at most n minus 1. So, number of mismatches is also n minus 1. Okay. The other way to see that the number of mismatches at most n minus 1 is that each time there is a mismatch, I shift the pattern by at least 1. Okay. Remember, there is a mismatch, I shift the pattern, right. So, I shift the pattern by at least 1. The number of times I can shift the pattern is at most n, okay, at most n minus 1. So, the number of mismatches, number of unsuccessful comparisons is at most n minus 1. So, the total number of comparisons is twice n minus 1, okay, which is what we had for those small examples, right, but this now shows that it is true for any example. All we need to do now, which we will do next time, is to compute this function f(x). Okay, once we compute that, we are through.